Okay, so it's a real pleasure to have Olya Ohrimenko from the University of Melbourne presenting to us today. So this seminar is at an unusual time because of the time zone difference. It's 8:30 in Melbourne, so 8:30 a.m. in Melbourne. So we're very happy to be learning about analog versus digital epsilons. So thank you.
Thank you so much. Thank you so much, Thomas, for inviting me. And thanks everyone for joining. I can't actually see anyone, or I can't see the chat either because I couldn't figure out the screen setting. So if you have a question during the talk, just please unmute yourself and say, or otherwise I'll just afterwards go through any questions in the chat. So yep, I'm a senior lecturer at the University of Melbourne, and today I'll be talking about two works. So one is a very recent one with Jan, Kyle, and Ben, and the other one is based on the work that I've done with my intern back at Microsoft. And the thesis work is in part supported by a Facebook Research Award and Osmurray Grant. So when talking about differential privacy, we are going to be talking about data analysis and the insights that we are trying to draw from doing a data analysis. So when do we collect the data, and when do we want to learn some insights from it? So we can consider, for example, census data, or the data that's collected about, for example, use of roads or public transport, right? So we draw some statistics and then make decisions on funding allocation or, for example, changes to the infrastructure that is needed. User data is also collected by companies, for example, to actually draw some insights in how this data is being used, and then to improve the services that are provided to these users. For example, by allowing, for example, for predictive text for me to use on my keyboard, for image recognition, or for some personalized services and recommendations. So then the question is once we do get to do these insights, how does the end user actually get to see these insights? Because they are obviously not actually getting access to the original data. So the way they kind of get access to this data is by, for example, having some API into it where they can run, for example, database queries on this data, and then instead of actually seeing the data, they get some statistics that is computed on this data. So here an analyst basically interactively interacts with this API. When we get to the kind of the machine learning model part of it, we see that there is some training data that we compute, that is collected, that is trained, and then the end user actually only gets the machine learning model, the final result that's computed on this data, and then it can just send the queries and get back, for example, predictions. So given that we kind of separated the data from our user, and that now our kind of end user has only, or analyst has only this API access into the data, then the question is, even though this data is kind of sensitive, is that good enough of a protection? And but unfortunately not. So as has been shown in several research papers, such release of data through this machine learning model still can be leaky of some private data. So for example, if the analyst is trying to understand if a particular record was part of a training data set, they can run what's called a membership attack. Whether some particular record has participated in a data set or not, whether it's leaky or not, well, it depends on for what purposes the data was collected. If it is the data of everyone who has a particular disease, then obviously if someone learns whether one record participated in it, they learn that this person had that disease. And actually, this type of attacks are exacerbated by models that have much more interesting APIs or much richer APIs, such as, for example, text prediction. As Caroline and others have shown that if there is a particular record that is participating in the data set, such as some very sensitive sentence, then actually can be revealed by doing kind of very specific queries into the model and getting it back out. And then later with my colleagues at Microsoft, what we showed is that also by having kind of access to the API of some model that's trained at some time t, and then a model that's trained later on in some later time, that one can actually, like by querying the two models, learn information about the delta of the data that was either removed in between the two models or added. Which is completely counterintuitive if I'm the user who asked, oh, can you please remove my data in between, and it is leaked as a result. So it seems that we cannot really get privacy by obscurity just because kind of our data is captured by these model parameters. So this is where we turn to differential privacy, which informally says that one data doesn't actually significantly change the outcome of the analysis. So the reason we like it is that it's a mathematical definition of privacy, and it makes minimal assumptions on adversary, because in practice it's quite hard to say what the adversary actually knows about the data beyond what is being released. We also rarely just analyze our data once. We analyze it several times, and differential privacy provides us with very nice mechanisms on how to compose and how to basically analyze several mechanisms at a time. So given that this mechanism kind of were proposed in 2006, where we are in 2021, so we're actually in a very exciting time where we are really moving from the textbook proposals of the mechanisms into the real deployments. So we see now with examples such as US Census, Facebook, and LinkedIn, where the data sets are, or where the statistics on the data sets are being released with differential privacy guarantees. And then with other companies, we see also the data being actually collected with differential private guarantees, such as in the local model, where the data already has some randomness in it. We also excitedly see that many of the big IT companies are providing open source open source libraries with algorithms, with differentially private algorithms. So I guess the incentive here is that even if you don't have a group of researchers working on DPs, then you can still use these open source libraries to analyze one's data with these guarantees. So since we are kind of in this very exciting process time where we are moving from the textbook implementations into the real deployments, the question is, are we there yet? And this is the goal of my talk, is to show that there are actually some implementation considerations that we still need to take account. And if we don't, then kind of the epsilons that we have proven on paper might not be the ones that actually hold when we actually implement these mechanisms in practice. So when moving in this process of showing that there are some implementations caveats that we are going to encounter, it is instructive to look at the textbook definition of differential privacy. So here we have two data sets that are neighboring, and the neighboring can be, for example, it's a difference in one user. Then what we are saying is that if we were to run a mechanism and we want to say that it is epsilon delta differential private, is that we say that basically the output, any output of this mechanism is quite likely for both of the data sets. So in the POIDP, we say that the two probabilities are basically just the multiple of each other, with delta being equal to 0, while in approximate DP, we say that there is some room for error that is captured in delta in between. A very important thing that I want to make clear out of this definition of what comes out of it is that if for one data set we have a non-zero probability of some output, while we just can never produce this output for another data set, this cannot satisfy pure differential privacy at all. While if the probability of this event for one of the data set is kind of non-trivial, then we would need also to have a non-trivial delta. And we usually want actually delta to be very small, such as 10 to the minus 6 or even smaller, so that basically when the privacy is broken with something really, really non-trivial. So when showing that how this definition of what are the assumptions that are made inside of this in the mechanisms that actually do satisfy differential privacy, where can things go wrong? So we will consider the following threat model. So we have our differentially private algorithms that are being kind of in this black box where the data is accessed, the compute is happening. Then we have our analyst. And our analyst sends queries F. It basically can choose adaptively which queries it's sending, and it sees different the differentially private protected outputs. So these are examples of the original systems such as Ping, UberSQL, Iravat, and actually one can even think that differentially private stochastic gradient descent is one example of this, even though one doesn't actually observe those randomized gradients, the actual analysis does assume that analysts could see them. So then inside of this black box, we have our differentially private mechanism happening where we analyze our data and we add some noise. So in this model, we assume that the attacker is the one who's trying to learn something about the data that's being actually computed on. So in particular, what it is trying to guess, it's trying to guess whether which one of two data sets could have been the input. Either it is D0 or D1, where we said that they are neighboring. And we are saying that we say something is a success here is when the attacker's guess is much better than what differential private had guaranteed. So it's much better than these deltas that we've already accounted for, or the kind of the differences, the probabilities that we accounted for. So something that would completely break this definition. So in this model, we will assume that the attacker does know the differentially private code, but doesn't know the randomness of the noise that was actually used. And it knows the two data sets and it sees the output, which basically is clearly the exact model that differentially private is set up in. We are going to look at three specific scenarios or three attacks in this threat model. And the first two are just purely on the noise that is being added. See that the noise is the one that's trying to protect our data. So we will see that this noise basically can suffer from floating point representation, and it can catastrophically break differential privacy. In the second part of my talk, we will look at some of the ways to actually defend against these attacks, and we'll see that they suffer on their hand from their own problems, which is based on timing. So in this model, it's quite clearly that the attacker, because they query this mechanism, they can actually measure the time it takes for the query to return the answer. And then finally, I will also look at how to protect against memory side channels for the attacker who gets to see how the data is being accessed. And I will come back on how this actually is getting observed by the attacker later on. So for now, let us just focus on the noise. So we will only focus in this part at the additive noise of the differential privacy. So here we have the function that we want to compute f, and then we add this noise. And we can either do it with either Laplace mechanism or Gaussian. So how to compare them? It's basically kind of like choosing which child do you love more. They give you very different guarantees. So from one draws Laplace noise from Laplace distribution and gives pure dp, epsilon dp, while the Gaussian mechanism does have this delta of that it could fail, but actually we see it being used a lot in the past few years because of its really nice composability properties. So when we want to analyze data multiple times, and this is exactly the model where in machine learning, where we are basically analyzing our data, computing gradients multiple times and so on. So whenever you want to query your data multiple times, Gaussian mechanism is basically your choice. So we will be attacking this noise, or we will be trying to attack it. And even if I lose you in the next few slides, let me just show you why kind of learning anything about the noise will actually break differential privacy. So suppose we have our users who are trying to hide whether they have eaten 2 or 5 chocolates. And they run it through this DP mechanism. And the DP mechanism adds some noise and returns 3 chocolates. So our analyst knows that the noise that must have been added must have been either +1 or -2. So what I will show you is that we actually create like a black box function where the attacker plugs in the noise that they can guess. So they either plug in 1 and -2, and they see whether this noise it was feasible to be generated. And for example, if this black box says -2 could not have been drawn, then the attacker straight away knows that it must have been the noise 1, right? So remember that I said the most important part of that definition is that there has to be a non-zero probability of seeing an output for all possible data sets or for neighboring data sets and for all possible outputs. Well, here we will clearly be breaking this definition if we were to know that some noise is not possible to be generated. So how can we do it? Why kind of the definitions don't capture it? Is that the distribution that we have been working on for Laplace and Gaussian, they actually are continuous distribution over real values. And I guess I'm not going to break anyone's heart to say that not all real values can be represented on finite computers, right? Because we only have some finite bits to represent the integer and the decimal part. And so in particular, for example, for 64 bits, we have the 11 bits for the exponent and 52 bits for the significand. And basically, by choosing certain exponent, we are also moving kind of the this dot between the integer and the decimal part. There are two important things about this representation of real values that I want to bring up. The first one is the number of possible floating points, which basically represent some of the real values. The number of real values that we can represent is unevenly distributed. So they are more densely distributed around 0, and the number of them basically gets decreased as we increase the intervals by ×2 and so on. So for example, looking at two same intervals as here from 10 to the 10 plus some small value and 100 to 100 to plus some small value, we see that now number of floating points basically decreases. So that's the first one important thing. Two is that not all values are possible, or actually posed otherwise as a children's riddle is why 6 should be afraid of 7. So if we were to actually print kind of the net or use Python's function of printing the next value, next floating point, we see that, okay, 0.23 is the next one, 0.25, and then 6 completely disappears, 8 also completely disappears. So 6 should be afraid of 7, because not just because 7, 8, 9, but because 6 also disappeared. What it means for us is that if there was ever a need to represent 26, it would be rounded to either 25 or 27. So what do we have? So we have these real values. Not all of them are represented, and they're represented as doubles on computers. So for some of them, we know that they're completely impossible. So our attacker could already use this information. But let us not when it sees the noise. But let us not forget is that the way we actually use these doubles in differential privacy is that we sample them according to some distribution, and such a distribution is Gaussian sampling. It's actually not magical, is that the way we actually generate or transform integers into doubles or random integers into doubles is that there is a computation that's happening. The way our attack works, and when it does this transformation, it actually uses such functions as trigonometric functions, logarithms, and square roots. And as you can imagine, this is what creates some of the rounding and imprecision. And this actually rules out even more doubles from the space of all the possible noises. And this is what allows us to create our attack. That is, we reverse engineer basically the transformation that's happening. So we take the noise values that our attacker is trying to see whether it actually is could have been produced by the sampler or not, reverse engineer it, see the potential integers it could correspond to, and then see if we were to plug it back into a Gaussian sampler, we have generated this Z or not. If we could, then yeah, it is a feasible noise. If not, then no, and differential privacy is basically broken because this output could not have been generated. So a very important thing to notice is that I'm not here assuming anything about the randomness, the source of randomness. It could be as random as possible. What I am saying is that what we are trying to distinguish is whether this transformation is actually feasible or not. So one intuition is how are integers actually, if I were to do a uniform sampler, forget about Gaussian, I was just doing a random int mapping into a double. I choose some random integer and I'm divided by a maximum int. And then in order to determine whether this could have been actually produced by this process, I will just multiply it by max int and see if this is a feasible integer or not. So with a very tiny example, if I had 2 integers and I had 4 doubles, and my attacker, for example, saw that the noise was 0.25. In order to check if this is a feasible uniform double value, they just multiply it by 2, they get 0.5. It's not an integer. So it could not have come from this particular sampler. So this attack actually was shown to be to work for Laplace mechanisms, for Laplace noise by Ilya Mironov in 2012. Which showed basically that yes, there are many doubles that cannot be produced by this Laplace sampler, catastrophically breaking this pure differential privacy. So then, even though it was kind of said in papers that maybe the Gaussian mechanism can be attacked, we have not seen in practice it being analyzed or having been shown that it can actually be broken with the Gaussian implementation. So this is the question that we try to answer with our work, and we answered it affirmatively by looking at several implementations. So why it is not as straightforward as just to apply a Laplace attack against Gaussian is because there is a very different transformation that's happening. For example, Box-Miller uses trigonometric functions. And the other important thing why it is different is because it actually draws two random integers in order to create the normal distribution. So it wasn't quite clear whether those attacks are just maybe in theory possible, as for example was shown in the concurrent work in Isorics this year, is that like how to basically do the reverse engineering of Box-Miller. So just to be for concreteness, let us see how the polar method actually works. So the main thing to notice here is that it takes two integers, or sorry, two double values, and then it transforms them into the normal distribution and actually produces two samples of the normal distribution, S1 and S2. In the implementation that we saw, one of these values is cached and only one of them is returned. So then the next time that you are calling this normal distribution, you basically would, if there is something cached, you return it. If not, you repeat the process. So our attack assumes that you know one of those values that was returned by the normal distribution, and then by this normal sampler, and then we plug in the values that the attacker is trying to attack, is to see whether this is a feasible normal value or not. And then we just see if this process could have produced it or not. So here one might say, oh, why would you, like, is it realistic to even assume that you have the second sample? So I will come back in a few slides. Why do we think that this is not so unreasonable?
By the way, are you assuming that you have the second sample without anything added to it?
That's a very good question. So in some of the examples, we assume that it is. In the others, we said, okay, what if you just knew, if you did the same mechanism second time, right? Then you would just know that it is the same value, so they will just cancel out.
I see.
Or you just run the query for which you would know the answer, so you can get it back as well. But okay, as I will show, for some mechanisms, actually not that unrealistic to assume that, for example, for when you're training a function, or when you have a function with multiple outputs, right, a k-dimensional function, then you would just get them by default. Okay, so what we did next is we basically tried to enumerate all the possible values that could have been generated by this process, by our own implementation, just to see the feasibility here. So here what we plot is for basically the output of differential privacy mechanism of what is how many of these values could have been in support of one database versus another one. So what we see here is we see a spike towards the zero. So there are many more attackable values. That is, if the attacker got to see them, they would straight away know that this is not the noise that could have been produced. So why is that? Why is it the case? Well, remember, as I said, there are many more double values next to the zeros than later on. So it's just much more likely that when we generate the noise, we end up to something that could not have been generated for the second database. So this gives us an indication that we should continue working on, or that we should have continued working on that. So now we looked at two implementations of Gaussian in NumPy and PyTorch. One was Box-Miller and one was the Polar method. And so what we did is we basically recall that our attacker is trying to distinguish two databases. So it basically runs our process on is feasible noise for one of them, for both possible noises, because it knows the output of the function of the differential private and the two databases. And we checked for the two databases that are different by two different sensitivity noises. So here the baseline is a random guess, right? Just by flipping the coin. So what we see here is two implementations. One is for NumPy, the straight line, and the dashed line is for PyTorch. And so on the x-axis, we see the epsilon, which is increasing. As you know, that means that the privacy is decreasing, and then the attack success rate on the y-axis. So interestingly, well, one is even for values of epsilon of 1. For example, for PyTorch, we get a non-trivial attack success rate. And I guess one of the reasons why PyTorch is kind of more attackable than NumPy is that it uses the Box-Miller method, which is trigonometric. So there is a bit more rounding happening when you transform the two. And then the other thing is, why are we seeing kind of the attack going up? Because it's not just because the privacy loss is actually increasing, but because we again end up with the noise that is drawn next to the zero. So we just get to see more attackable values. So then we looked also at where this Gaussian mechanism is actually used for differentially priced stochastic gradient descent, and we looked at the library in PyTorch maintained by Facebook called Opacos. So here, what our attacker is trying to distinguish is training basically a machine learning model on two batches of data of MNIST. In one of them, basically the record that they're distinct, or that they're different in, is in just one value. So in the D1, the only difference is that there is a 0 and it doesn't have a 0 in the other one. So this should still be covered by all the clipping that one does, because it still corresponds to the training data, just not in that particular batch. And so what we see here is on the top axis again, epsilon, except it's going down, and then the success rate on the y. So we see that the floating point attack does work on distinguishing these two batches as well. And the success rate goes down as epsilon goes down, which was similar what we saw in the non-DPHDD setting. The main difference with the previous graph here is, as I said, that here our attacker actually gets more than one value back. Is that when we are actually doing this DPHDD, we are not computing just one function. We are computing a gradient for all the different parameters in machine learning model. So here our attacker just sees how many values are in support of one versus another batch and then chooses them. So this brings me to this, I guess, question also that Thomas was asking is, well, so how feasible it is for us to assume that one has the second value. So first of all, it would work for if f is k-dimensional, which is the case for DPHDD model. It could also work if the attacker shares a library that just gets to access the cache of this library by just probing it. And I guess theoretically, if we are, for example, on somewhere with a very small precision, then one could potentially enumerate all possible normal values, while it might not be as likely for 64-bit precision. So what are the main takeaways of this first part of my talk is that floating point attacks do work against Gaussian samplers in practice, and we use PyTorch, NumPy, and Opacos implementations for that, to show that. And they also work for some of the more common uses of differential private, which is, of Gaussian mechanism, which is DPHDD. So what are the possible mitigations? So one of them is to just drop the value of the Pola and Box-Muller, because as I said, they all assume 2 samples. However, there is another method for generating it, which is the Zugarat method, and our preliminary results show that they are also susceptible to these floating point attacks, because really, in the end of the day, it's just a transformation, and this transformation just suffers from rounding, and you just can't generate all possible doubles on the other side. The other method that was proposed in this concurrent work from Isorix, as I mentioned, is just basically using this divisibility property of distributions, and instead of adding one normal noise, just add multiples of them. So it's not quite clear what would be, I guess, the theoretical guarantees, because you still would get the rounding effect. Then there was also the snapping mechanism that was proposed by Ilya Mironov in his attack, is basically by now rounding some of the noise and accounting for it in the epsilon guarantee. However, shown in NeurIPS last year is that the utility can actually drop, because we are adding constant factor of the original noise. So given that all these 3 methods above are still kind of having to deal with all these defects of floating points, why don't we just move on completely from that and look at discrete variance? So stay tuned, and this will be part 2. So, but before I go on, are there any questions about this part? Okay, so in the first part, we saw that some noises are just not possible because of the floating point representation. So one way of completely removing that is going away from the continuous distributions into discrete. But what we will see is that with these discrete representations, we actually get to observe, we might create another side channel, which is due to the timing. But actually, it can be forced or can be done by an attacker who is querying the mechanism and then gets to see the output and measure the time it takes for the query to return. So timing against differential private mechanism is not kind of novel and has been considered before. However, it was considered on the timing of the actual function on the data that it takes, but not on the noise that's being generated. So in the work called DP Under Fire, where they propose this fast system, they basically timed the amount of time that it takes to evaluate some predicates inside of the function. And whether this predicate is true or false would reveal some information. In another work, actually, there was also an attack on floating points, but on the floating point operations. So as you can imagine, multiplying by 0 while multiplying 2 very different floating points will take much less time than in the latter case. So they've used that in order to show attacks on differential private mechanisms. In our work, we are also talking about timing, but instead we are measuring the time it takes to generate the actual noise. And we'll show, because you can basically correlate the time it takes to generate the noise, you learn the noise, and hence you break the differential privacy guarantees. So, as I mentioned, one of the ways to protect against this whole floating point business is to look at the discrete versions. So when working on discrete Laplace, researchers have have observed that Laplace mechanism is basically a 2-sided geometric distribution. So one can draw a sample from a geometric distribution of some magnitude, say V, and then use that to convert it to some Laplace noise Z. But when doing this conversion, the magnitude of the noise of the geometric distribution is still present in Laplace. So in case you forgot what geometric distribution is, remember that it is basically the probability of taking V Bernoulli trials, right? So we flip. So how do we actually kind of measure this geometric distribution? So we can, in real life, right, flip coins. So Australian coins are quite fun to flip because you get to see these cute animals like platypus, echidna, kangaroo. And our banknotes are even more fun to flip because they're very colorful. But the main point is that it takes time to do these trials. And the time that it takes to do these trials both in physical and in the digital world, is directly proportional to the number of trials that one is doing. So there are two ways that we saw the geometric distribution can be sampled. In the first one, or in implementations, in the first one, we basically choose a random double, and then we check it against the bias with which we want to flip the coin. And we either go left or right. So we either say, oh, it is a successful trial, and we exit. Otherwise, we go on the other side and we flip again and we repeat the process. So see that the number of times I'm drawing this random double is directly proportional to the number of trials that I'm going to do. And this is basically the value that a geometric distribution is going to sample. In the second implementation that we saw is something that resembles basically kind of a binary search using cumulative distribution, where again time draw some random double noise, and then I go either left or right depending on how likely the values are, or how many values are distributed in one part or another. But the main takeaway is that the number of searches that one does and the magnitude of the noise are completely correlated. So this is in theory. Can we actually measure it, or maybe these random doubles are like super fast generation, and so we can't. So for that, we looked at two implementations. One is just the research code from the New Rips paper from last year, and one is from the Google Differential Private library. And we mentioned to the authors of this that basically, there is the correlation between the noise value, which is the axis value, and the time it takes to generate it. And so for the first one, we saw that for both, it holds for discrete Gaussian and discrete Laplace, while in the second case, it holds for the discrete Laplace. So there is some difference in between the actual magnitude of the noise in microseconds. So one is the first one, there is an order of magnitude kind of difference, but this is probably due to the language that is being used in the format Python, and the second one is Java. So this is just kind of like a small, an example if one was to measure the noise. But in practice, what we are trying to do is we are trying to see if this noise is actually enough to reverse engineer of what the actual data set that was used by differential privacy. So here we now looked at what if one measures kind of end-to-end, summing up some records or some values, and then adding the noise and measuring the whole time. So here we did that for two different data sets that differ either in sensitivity by 30 or by 50. And here we see that there is indeed a correlation with the success rate as epsilon goes up. But the main thing is that if our baseline is a random guess of doing 50-50, our attack success rate is higher than that. So we can actually exploit this if our attacker does get to observe the time it takes to do the measurement. So how can we mitigate? So the mitigation that was proposed by Thomas and the other authors is to run the algorithms until some maximum time, and then to actually capture this kind of, if you were ever to go over that threshold, is to capture this failure in the delta part. Another way you can think of is basically maybe doing some caching. So we could offline generate some of the samples and then use them as for example, in the Gaussian floating point value one at a time. So the main takeaways are that if discrete samples rely on this geometric distribution, then the time it takes to do the samples actually reveals the magnitude of noise. I have to be very open about the limitations of the attack is that if we were to do multiple of those, as we would need to do for the DPHGD, then one might only measure, for example, the maximum time it took the noise or the total time, and it might not be enough to actually do use this attack. It is also important to note whether maybe the mechanism itself might be very, very expensive in terms of time, and then the addition of basically in microseconds of this noise might not be measurable, or that the network signal is not strong enough. However, there are quite a few attacks showing that even basically 10 microseconds of a difference can be observable over the network as well. So I'm now the 2/3 into my talk, and I'm gonna now move on to a different side channel on memory side channels. But before that, I'll just pause and see if there are any questions on this part.
What scale were you running the noise at for your experimental results? So you had one thing that said, the correlation between the absolute, this one. Like, what is the scale parameter that you were setting this to run at?
That's a good question. I will need to look at the paper. So for all of them, I think we tried like with epsilon of 1. And then what exactly that sensitivity contributed, I don't remember from the top of my head, but I'll get back to you later on that. I think it was, all quite reasonable, basically, because all of the noises are possible, right? So we would run just 10 million of trials and measure all of the time, all of basically the time that it takes for all of them to generate. So I think as long as the epsilon is 1, right, we just measure all the times that all the noises that are possible.
Right, I see. Yeah, I'm just sort of curious, like, is it the large noise regime or the small noise regime where it's more sensitive to where this attack is more likely to succeed?
That's a good question, and I think this is kind of maybe what's shown in this graph is basically what our attack is doing. Is it's doing a classification problem, right? Is that if you were to observe some noise, if you were to only observe several noises, you'll have much better measurements of the a priori ones, right? But if your noise is much more distributed, as we see, for example, for the sensitivity of 50, then you actually get kind of worse attack because, there is just much more variability. So I think it was kind of more of a small noise, to answer your question, that where it is attackable. But I'll get back to you with the exact measurements later on. Okay, so we kind of, in this first part of the talk, we looked at all this kind of the noise generation and how to attack the noise. In the last part, what I will look at is that it's not always the case that kind of the actual generation of this differentially private mechanism is going to be happening like in the US census, for example, on their own data centers. And given that we are seeing a lot of these open source libraries that are coming up, we actually, hopefully, the big vision is that one day we'll do all of our data analysis using differential privacy, and we will be using cloud services for that because not everyone has all the computing resources. And given that we are going to be using these differentially private algorithms on the cloud, it's probably likely that we are dealing with very sensitive data, and so we will be using high security protections such as encryption of the data and then processing them using trusted execution environments. And this is actually the model that was proposed by Proclo on basically even shuffling the data using, for example, trusted execution environments and some of the deployments of LDPs that we were suggesting in our work with my Microsoft colleagues. So we are now in this model where we are deploying differentially private algorithms on the cloud using this trusted execution environment. So the question is, what is still being observed? And if you've been following trust execution environment literature, there's a lot of attacks on side channels. And one of the ones that worries the research community a lot is memory side channels. Why are they possible? Because we are still in this shared untrusted environment where there is the OS, where there are other users of the cloud that we could be sharing the cache and so on. So what can they observe is basically the addresses that I'm accessing, which data points I'm accessing. And if you might ask, well, can these addresses reveal anything? Well, in this paper at Auckland in 2015, they also showed that if you are just decoding an image, then you can basically reconstruct it pretty well. You can't reconstruct the colors because the colors are encrypted, but you can actually reconstruct it by just knowing when the same color is being accessed multiple times. So how does this actually apply to differential privacy? Well, the question that we want to ask is how is the data actually usually processed and kind of what is the blueprint of accessing the data. And the specific case we will look at is in machine learning, where we do some mini batch training. We basically take a data sample and then we update the model. We then take another sample and we update it. So we operate on these samples of the data, and you might think, oh, this actually sounds like it might give some privacy, right? Because my data is only used in one of these samples. And actually, differential privacy really beautifully captures that in this privacy by amplification, which says that if I did have a mechanism that was epsilon delta dp, if I instead applied it, instead of all my data set, I only applied it on a random secret sample of this data, I would actually get better privacy guarantees by analyzing something small. And this is captured by basically the size of the sample. So if the size of the sample is 0.1, I get 0.1 roughly times epsilon. So I get much better guarantees by analyzing this small, basically this small sample. So then the question is, how are these samples being generated? So in practice, most of the machine learning model frameworks just shuffle the data and then split it in the batches. So no batch contains the same record. But actually, in order to use this privacy by amplification results, we need to assume that the attacker doesn't know whether the same record has appeared in more than one batch. It's basically, privacy is amplified by this plausible deniability, whether the sample could have, the record could have been in a sample or could not. So there are interesting samplings, such as sampling without replacement, whether the record can appear in more than one batch, and there are also other sampling mechanisms. So when we start analyzing them of what epsilon dp or epsilon delta they give us, with shuffling, if we were to just analyze a single batch, because we don't have this plausible deniability, we get just epsilon of analyzing this sample. And then with sampling without replacement, we actually do get this nice guarantee of gamma, which is basically the size of the sample. We rarely analyze just the batches. We usually analyze the whole data in a whole epoch. So now we can apply other mechanisms such as parallel composition or strong composition to analyze how what is the privacy loss if we were to do multiple batches. So the main takeaways, forgetting about all the square roots and the gammas here, is that we get better privacy guarantees if we were not to do shuffling. However, in practice, everyone shuffles, and if we were not to shuffle, or if we were to sample, the sample must be hidden. That is, we can't reveal whether the two samples contain the same record or not. And if we didn't, then we wouldn't be able to use this privacy by amplification. So when we started looking at it and looked at how DPSGD is actually implemented in research papers, we saw that for some in the analytical section, it would be the Poisson sampling used, while in the experiments, it would be, for example, shuffling. So then the question that we try to answer is, how can we generate these samples, one, efficiently? Can we generate them all at the same time and not incur, for example, some of the costs that we could incur using, for example, black box usage of protecting against memory side channels? And how can we do it basically privately? And what do I mean by privately? Is by hiding how we generated the samples and protecting against memory side channels. So what we have proposed is this mechanism, which we call data oblivious sampling, is by generating all the samples basically in one go, so then you can parallelize or analyze them however you want. Why do I call them oblivious? Is because whoever observed how exactly I generated them would not be able to say whether two samples contain the same record or they didn't. This is actually quite not a straightforward process to do it. Is that if we were to do it naively, one can basically, if they were to observe, for example, how I generated sample 1 or sample 2, they could see kind of just me accessing the same record twice. They would see which samples contain that. So we would not be able to use this privacy by amplification result when basically saying what are our end-to-end guarantees. Instead, we proposed a mechanism which is at very high level, basically works by scanning all the records deterministically and replicate in a record based on the number of samples that it has to appear. And then finally, also associating each of these records with basically the sample ID of where it should appear, and then obliviously shuffling them. So kind of the takeaway of this part is that we definitely get better privacy guarantees if we were to do this sampling than shuffling. And we propose an efficient and simple algorithm to do that, which basically just operates on 2 oblivious shuffles and 2 scans. Since our work in 2019, I have checked this week of how actually this sampling is implemented in TensorFlow, Privacy, and Abacus, and I saw that there are now implementations for boson sampling and sampling with replacement. However, at least my understanding is that generating each sample, it still takes order of n, where n is the size of the whole data set, by basically drawing a random probability and then just either taking a sample or not. While our approach is trying to generate all samples that are possible from this data in one go and basically amortizing this cost and doing all the samples in order n. So it would be interesting to see actually if one is, if it's more efficient to do it basically by doing it in an amortized way. So in summary, I think we are in this exciting process where we see basically real life deployments of differential privacy. But when doing so, we should still be careful in which kind of Gaussian samplers, for example, we are using, and where we are actually seeing these differentially private algorithms being deployed. For example, if it's in trust execution environments, ensuring that they are protected against memory side channels. And actually, many of these attacks start resembling us that differential private code is almost like crypto code. One does not roll it out themselves, and maybe when we actually create it, we also need to harden it as well as we harden the crypto code. So this work is joint work that started with Eleanor last year, who was still at Melbourne University back then, with Jian Kai, who is my PhD student, who I supervised with Ben Rubenstein, and the part on the oblivious sample was with Sajjan, who was my intern back at Microsoft. So with that, thank you.